In this video, we're going to do an introduction to combination, so 2.6. Up until this point, we have been talking about permutations. And permutations are where we're counting the possible arrangements where the order of those arrangements mattered. So that is to say that if we have a number of objects and they're arranged in a different order, we'd count that in a different set because, as I said, order matters. However, for combinations, the order in which things appear is not important. Let's take a look at the first example. Example 1. In how many ways can you arrange 2 letters from the word fun? Well, we know that there are 3 letters in the word fun, and we're arranging 2 of the 3 letters, so that is 3 permute 2, and of course we know that that would be 3 factorial over 3 minus 2 factorial, which is equal to 3 factorial over 1 factorial, which is just 6. Now, of course, in mathematics, it's always better form if we take our terms and we write them beneath when we're doing algebra. I just didn't have very much room here on the page, but in your notebook, it'd be a good idea to do that. Okay, moving on. So, what if the order did not matter for those 2 letters arranged in the word fun? So here I've written out all the possibilities for arrangements of 2 letters from the word fun. As you can see, I have 6 down. FU, UF, FN, NF, UN, and NU. So those are all the possible arrangements. However, if we didn't care about the order, so that's what we're asking here, FN and NF would be the exact same because we don't care about the order. All we care about is taking those 2 letters. So we'd actually cancel one of those. And of course we'd have to do that for these other cases too, and we'd only be left with 3 combinations. And of course that makes a lot of sense because each selection of 2 letters will have 2 factorial possible arrangements, and we don't want those, so we will have to have 2 factorial times more arrangements than selections, so we're just going to divide those out. So if you notice, we had 6 and we divided it by 2 because we had, divided by 2 factorial because we had that many more arrangements. We don't care about those, and we're left with 3. Now, let's come down here so we can talk about that in general. Okay, so in general, the number of combinations of R objects chosen from a set of n distinct objects is n CR, where you can write that as C bracket NR, so that's one way, or you can just write it in parentheses where you have the N on top and the R beneath, and that is equal to this right here. So you can see it's very similar to the permutation formula that we know, where we have N factorial on top, N minus R factorial on the bottom. And since we don't care about the order, we only care about what we're pulling out, we don't care about how they're arranged, we're going to divide by R factorial. So that's exactly what we did in our example with the word fun. We divided by 2 factorial because that's the number of letters that we were pulling out. So however many items that you're pulling out, you're also going to divide by that number factorial. Another way that people tend to think about combinations with respect to permutations is they think about it like choosing. So you're choosing a specific number of items from a larger set of items, and you only care about what you're choosing. You don't care about the order in which you're choosing it because there's no organizing or arranging, it's just what you're choosing. So sometimes when you see NCR, that can be said as N choose R. So from the n total items, you're choosing R of them, and we care how many different ways you can choose those. Okay, so now we're going to take a look at example 2. In how many ways can the following cards be chosen from a deck of playing cards if order of selection does not matter? So In part A, we are wondering how many ways we can select any 4 cards. Now, a deck of playing cards has, of course, 52 cards, and we're just interested in selecting 4, where the order doesn't matter. So that would be 52, choose 4, which is, of course, equal to 52 factorial over 52 minus 4 factorial times 4 factorial. Now, when I plug that into my calculator, I get 270,725. So there are a couple options here when you're typing things into your calculator. You could put it in exactly like this with factorials and do it manually. Or you can go to your math function like we did when we were looking for the permutation button, and you will find an NCR. So you can use, you can go straight from 52 choose 4 to your answer here. Okay, so let's move on to part B, 4 diamonds. So in the deck of cards, there are 13 different diamonds available, and there are 4 that we are considering choosing. So we have 13, choose 4, and I'm just going to write this out for practice. So that's 13 factorial over 13 minus 4 factorial times 4 factorial, which is equal to 715. Now we're going to take a look at part C, which should be on the next page of your booklet. So we're looking ways to choose 2 kings and 3 queens. Well, in a deck of cards, there are 4 different kings that we can choose from, and we are looking to choose specifically 2. So that is 4, choose 2. And since we're looking for and 3 queens, we're going to multiply that by 4 for 4 queens, choosing 3 of them. And once I type that into my calculator, that's going to be equal to 24. Part D, 2 spades or 3 hearts. So for the 2 spades, there are 13 spades in the deck. We're choosing 2 of them, so 13, choose 2. For the 3 hearts, there are 13 hearts. We're choosing 3 of them, so it's 13, choose 3. Now because it's or and not and, we're going to add these 2 cases. I want to make it very clear as to why we do that. When we have and, for every possibility that we have here, so every possible combination we have here, because there's and, we also have to arrange them or combine them with these possibilities here, and we do that via multiplication. So these are options that we're multiplying. These, because it's or, so you can either get 2 spades or you can get 3 hearts. Those are 2 different cases, and whenever we have cases, we should know to add those, okay? And that is equal to 364. And finally, part E, 4 aces, 3 kings, 2 queens, 1 jack, and 1 other card. Now, what's really important to notice here that this is and, so we know that when we're considering all the different combinations, we're going to multiply in between them. So for the 4 aces, since there is, of course, only 4 aces in the deck, that will be 4, choose 4, multiplied by 3 kings. Well, there are 4 kings total, so that's 4, choose 3, multiplied by 4 queens, choosing 2 of them, multiplied by 4 jacks, choosing 1 of them. And then for this 1 other card, we need to consider all the other cards in a deck. So we specifically don't want to choose an ace, a king, a queen, or a jack, because if we did, then instead of having 2 queens like we wanted, we would have 3 queens. And the question specifically asks for 2. Now, of the cards that we haven't chosen from, there are 2 through 10 in terms of denominations, which are 9 different denominations. And then we have to include the fact that there are 4 different suits. So that's 9 times 4, which is 36 options. And then 36 choosing just 1. So that is 36. Well, choose 1. And so when I write this all out into factorial form, using our formula that we know, we can see that things become a lot simpler. So in our first case, where we have 4 choose 4, and we have 4 on the top and then 4 minus 4 on the bottom. Well, 4 minus 4 is just 0, and then 0 factorial is just 1, so that just is 1. And then 4 factorial over 4 factorial is also 1, so that's just 1. So 1 times the rest of everything else. We don't really need to include that in our calculator because that's just the same. And then our second term can become simpler as well because the 4 factorial and the 3 factorial cancel themselves out, where we just have 4 left because the 3 factorial cancels the 3 times 2 times 1. And then 4 minus 3 factorial is equal to just 1. So that's just 4 on the top now. And then over here, the 4 factorial and the 2 factorial, that'll cancel out the last 2. So that's just 4 times 3. And then we have another 2 factorial because it's 4 minus 2. And 4 minus 2 is 2 factorial, which is 2. And then 2 goes into 4 2 times, and so we have 2 times 3, which is going to be 6. 4 minus 1 is 3 factorial. 1 factorial is just 1. We're going to cancel out the 3. We're just going to be left with 4 again. And then the last one, we have 36 minus 1, which is 35 factorial. So that'll cancel everything except the 36 in this factorial. And then 1 factorial is just 1. So when I'm typing this into a calculator, I could either type in this line, which is fine. I could type in this line, or I can type in 4 times 2 times 3 times 4 times 36, which is equal to 3,456. On your own, try example 3 for homework, and in next class we will take it up.